Okay, guys, welcome to week 4. So let me give you a rundown what the next few weeks is going to look like. We only have 3 more weeks of new curriculum. So these next 3 weeks will roll out 3 sets of weekly objectives, and then you'll have that 4th week to make up any of this work that you haven't done. If you're still needing points to get your grade up, then me, Mr. Martinez, Mrs. Bouchard, we will find ways to help you get that grade up if you still need it. Okay? But we're only going to do 3 more weeks that are similar to what we've been doing so far. Okay? So let's get into this week. We're going to look at some different structures. We're going to look at evolution, natural selection, adaptation from the standpoint of body structures, and some pretty interesting stuff. So the first question you have on your objectives this week, on your notes, is what are homologous structures and how do they fit with evolutionary theory? And then we're going to look at some examples. So homologous structures are anatomically similar structures that are inherited from a common ancestor. Okay, so anatomically, that means that they're structured, put together in a very similar way, and they've been inherited from a common ancestor. These are homologous structures. Well, how do they fit with evolutionary theory? Well, they show common ancestry. So sometimes we'll use words like strategies when we're talking about biological fitness, like we mentioned last week. If a trait is favorable for the survival and reproduction of an organism, then that trait's more likely to be passed on. Well, sometimes these traits they become very pronounced or obvious, like the long neck of a giraffe or the wings of a bird or something. And we sometimes will use the word strategy. This is an evolutionary strategy. So these structures kind of show that somewhere along the evolutionary chain, this setup was favorable, and it benefited the organisms that had it, and then it was passed down. And as they diverged and went into different habitats, different environments, and over millions of years, different species would evolve in different ways to suit that environment, that specific environment, the specific habitat where they live. But these structures that are homologous, what they show then is evidence of common ancestry, that specific anatomical pattern or setup was there a long time ago, and it's been passed down. And even though these species have diverged into different areas and done different things, there's a common ancestry there. So what are some examples then of homologous structures? So we're going to look at a few right here. And what you see on your screen is the skeletal structure of a human arm, the leg of a cat, the flipper of a whale, and the wing of a bat. And what you'll notice is a very similar anatomical pattern or setup. If you look at the human, the cat, the whale, and the bat, they all have one single upper limb bone called the humerus. As you work your way down, then there are 2 bones, the radius and the ulna. And then you get to the carpals. We would call that our wrist. And then the metacarpals, that's like the palm of your hand. And then the phalanges, and those are your fingers. So if you look at the human, the cat, the whale, and the bat, they all have this same setup, this same structure. Now, there's some key differences. If you look at the whale and the bat, their phalanges are much longer, right? But it's the same basic setup. And so that's why we call these homologous structures. Okay, so the next question is about vestigial structures. So vestigial structures are reduced form of some structure that used to have a use or a purpose for that organism, but no longer does. Okay, so it's a reduced form of a structure. It used to serve a purpose for that organism, now it doesn't. So real common examples that we use are like an appendix in humans. It's a little organ that hangs off right near the connection between your small intestine and your large intestine, down the right side of your abdomen, lower right. And it doesn't really serve as much of a purpose for us anymore. You can live without it just fine. You don't really need it. And so most scientists think it used to aid in digestion in some way, maybe an area for bacterial colonies to form, those symbiotic bacteria that live in our gut that help us digest our food. But in modern humans, it serves no purpose. You'll also find things like a pelvis or femurs in whales and snakes. If you look at your picture right now on the screen, you'll see that this whale has a pelvis and a femur. So it's got this sort of reduced, sort of leftover parts that used to serve a purpose in its ancestors but no longer do. In fact, they're completely hidden inside the body, little tiny leg bones, even though they don't stick out at all on this whale. And you see similar things in snakes as well. And so vestigial structures, they also point to common ancestry. Okay, that there was a common ancestor somewhere along the line of, and we're looking at a lot of mammals today, that had this same sort of setup, this same structure. But as the organism found new strategies, new ways to survive, as it moved into new environments, new habitats, the species changed over many, many, many years. We're going to look at analogous structures. Analogous structures. And so these are structures that organisms have that can be used for the same purpose, but they aren't necessarily built in the same way. They're not anatomically similar structures. They're not like homologous structures. They do not point to common ancestry. Okay? What they point to is that different organisms from different evolutionary lines find similar strategies sometimes when they're faced with similar challenges in similar environments. So if you look at your screen on this one, you're going to see several different wings. Got the wing of an insect, like a moth. I'm guessing that second one's like a pterodactyl wing, even though it's not labeled. Then a wing of a bird and a wing of a bat. Now, all of these wings are used for what? They're used for flying. They do the same purpose. But none of these organisms are closely related. And these structures aren't built in the same way. Let's focus on the bird and the bat really quickly, the two on the right. So what you see is the bat, that setup that we talked about, that bone structure that we talked about. But what is a bat's wing made of? It's made of skin stretched over the arm bones, basically. And specifically like the finger bones, the really elongated phalanges. And that's what makes up the wing. Whereas on a bird, the bones make up sort of the anchor for the wing, but then the main structure of the wing that gets all the surface area for flight are the feathers that hang off of the wing. Okay, so they're put together very differently, but they just serve the same purpose. So these are called analogous structures. Okay, the final thing we're going to look at is comparative embryology. So the question asks, what is comparative embryology and what insight can it give us on the relationship among different organisms? So we know what an embryo is, right? This is the developing form of an organism before it is born or hatched or whatever, right? It's an embryo. It's still in its egg or still inside its mother if it's an organism that gives live birth like we do. and so it's a developing organism. And so you can look at structures of embryos as they develop at different stages of development. So if you look at the picture that I put for you now, there's several different organisms: fish, salamander, tortoise, a chick, a rabbit, and a human. Okay, and if you look up at the first, the pictures at the top, they all look pretty similar. I always have tough time saying that word, similar. And all of them have those little slits. They're called pharyngeal pouches. And so at that stage of development, that first stage of development, they're all very similar. Now in fish, those pouches develop into gills. In mammals and birds and reptiles, those pouches develop into parts of the ear, throat, and jaw. So what you have are structures that are homologous at one point in the development of the embryos, but then they drastically change while the organism develops and fully grows. And you can see how much different they get as they go along in the picture that I have for you. So what does this point to? So for scientists, they believe that this also points to shared ancestry, that first stage of development that's so similar for so many drastically different kinds of organisms shows some relationship somewhere way back on the evolutionary chain. So I hope this was pretty clear for you. This is starting to getting to be some pretty complicated, tough stuff. Okay, but it's very interesting. If you have any questions, reach out to us. The readings should be posted for you as well. We love you guys. We miss you. We're almost through this. 3 more weeks, and just hope to see you soon. Hope to see you next fall, and we'll talk to you soon. All right, bye guys.